Okay, let's start today's tutorial. So at first we will talk about some basic concept and the basic concept about the description of microcanonical ensemble, canonical ensemble and grand canonical ensemble. So maybe I have told you guys previously in the previous tutorial also, but let me repeat it because I will need some concept from here. So let's first deal with the microcanonical ensemble. Micro canonical ensemble. So in this course, statistical mechanics, this concept is used in every lecture. So to express a microcanonical system, the way you can express a microcanonical system or any system, you can express it in three ways: one microcanonical, second canonical, and third grand canonical. In microcanonical, you have to specify the all positions and momentum, that means the states of the all particles of which you want to describe. So you have to specify the all energies or all the states of this system. So we define the microcanonical ensemble by its entropy. And how? E to the power s u n is equal to summation of all possible combinations of ni delta 0 u is the total energy minus summation of I epsilon I ni and another delta function which is for the conservation of total number of particles ni. Okay, let me write it in this way. So the first delta function is for the total, since the total energy of the system is conserved. Since the total energy of the system is conserved, total energy of the system is conserved, and the second one is the total number of particles is conserved. Total number of particles is conserved. So in microcanonical ensemble, we have to specify the what amount of particles are sitting at the which states, and so we have to specify the what is the number of particles sitting at every state. I is the possible number of state and ni is the all possible combination which keeps the total energy of the system conserved and the total number of particles is conserved. So this is the description, is called the microcanonical description of an ensemble. Now as we know that we can describe the same system, and to describe the same system in canonical way, canonical means its Legendre transformation of this microcanonical ensemble is actually called the canonical ensemble. And we know that in by Legendre transform we just remove one extensive variable by an intensive variable. So here we remove this extensive variable u, and in place of we will use the description by the temperature, which is an intensive variable. So intensive variable. So in canonical ensemble we just Legendre transform of this form, and by Legendre transform we mean that we will replace one extensive variable total energy by intensive variable. Now to do so, if you do so, you will get the partition, which is called the partition function, is equal to du e to the power minus beta u. Since I want to and delta 0, okay, so I want to e to the power s u n. So this is z is nothing but the Legendre transformation of this quantity. Legendre transformation of this quantity, e to the power beta u e to the power s union. Now so this will that, and if you express it in terms of summation, you can write it the same thing. In for continuous energy space you will write the partition function like this, and for discrete state space you will write the partition function like this: beta I epsilon I ni delta 0 n minus summation of I ni. So now this is for, okay, let me rewrite it so you will get it. So not it, okay, let me rewrite it. Here I was wrong earlier, I was wrong. So you will just put the form of e to the power s un. So that is basically summation of all possible combination of ni's delta 0 u minus summation of I ni epsilon I, and another delta is which is 0 n total number of particle minus summation I small ni. Now if you integrate this du, you will get this result. So summation over all possible combinations of particles in ith state into e to the power minus beta. In place of you have to write ni epsilon I. So I will write summation of I ni epsilon I into delta 0 n minus so I ni. So this is called the partition function. It's called the partition function of a system which is in temperature T or 1 by beta. So that's that. So we will use, rather than using this microcanonical ensemble, for many cases it is very useful or very useful to use it Legendre transform form, which is the partition function. Now in this tutorial I will use this partition function many a times. So let's begin. Let's solve the question number 1. So let me insert, okay, the question number 1. Yes, so in the question number 1 it is asked that consider the Ising time model h equal to minus j equal to 1 to n si plus 1, and this is for periodic boundary condition. But now imagine that si can take values 0 1 for each I equal to 1 2 3 n. Now we have to write the partition function for this system and the transfer matrix. So let's begin. So as we know from our previous exercise that the partition function is nothing but the all possible arrangement of the number of particles and e to the power minus beta into total energy, which is Hamiltonian, and the total number of particles are automatically conserved here. So total number of particle we are not considering here the total number of particle explicitly, but this total number of particle constant should also be there. Now it is summation of ni e to the power minus beta j summation of j I equal to 1 to n si into si plus 1. Now suppose that this e to the power minus beta j si plus 1 can be written as a matrix, written as this is the matrix element of a matrix si plus 1. Its si plus 1th element is e to the power minus beta j si plus 1. Then this T matrix is called transfer matrix. So now if you write this summation in terms of this transfer matrix, you will get summation of all possible combination of ni. Here this will not be ni because in place of ni this will be si, because here the possible combinations of the spins will be there, not the total number of particles. So it will be si so this can be written as first term s1 s2 t s2 s3 t s n plus 1. Since we use the periodic boundary condition, Sn plus 1 is nothing but S1. So let me write it S1. Now since this is the all possible combination of all i's, that means, and since from the Hamiltonian we can say that only the nearest neighbor depend on each other, that means this summation can be taken inside. First let S1 be there, and this is T S1 S2 and T S2 S3. Now we can use the summation all possible combination of S3s to do this and then t, and there are also other summation also be there, which is not s1 and s2 but all the j, which is j not equal to 1 and 3. So this will be s ts3 t4 dot 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 tsn s1. Now from this is the matrix multiplication. Now this is the matrix multiplication, then this will become simple matrix. From the simple matrix multiplication rule we know that, so this is I need, this is not s3 but I need, it should be s2, so this should be s2 and this is 2 and 3. Okay, so though if we sum over this s2 we will get a element of t square matrix. What will be the element? s1 s3. Now again I will sum s3 and this will be t s3 s4 dot dot dot, and this will be a summation over, so this is a summation of j not equal to 1 2 and 3 t s4 s5 dot 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 t sn s plus 1. Now from this and this again a matrix multiplication matrix multiplication rule, and if we summing over this s3 we will get s1, this will be t cube whose element will be s1 s4. Now similarly if we do these things again and again, at last we will get summation of s1. This sum will this sum will not used by any of this matrix multiplication. Now since there are n elements, so that means I just summing the 3 elements, it gives me the t cube. If I summing the n element, it will give me tn and s1, and the last index will, since we summing over this and the last index will remain, so there means the last index of this will remain. That means this is nothing but the trace of transfer matrix to the power n. Since we know that trace means the all diagonal element, diagonal element means it's this index, this means tii, which is nothing but s1. So that's that. Now here we know that what is the transfer matrix. Here the transfer matrix is si plus 1th element is e to the power, so minus beta j, so here it will be plus, so here it should be plus because 1 minus is there, so it should be plus. Okay, so here I knew that, here we know that it is its si element is beta j si plus 1. Then we can write the whole matrix T by using the values of si and si plus 1. So what value the si and si plus 1 can take, they in the question it is it has already given that the si can take value 0 and 1. So let's put that value 0 and 1. If we put both values 0, so this will become e to the power 0, which is nothing but 1. If we put 1 0 and 1 0, si 0 and this is 1, then also it becomes 0, that will become 1. Similarly here also it will become 1, and the last element where si and si plus 1 both are 1, it will become e to the power beta j. This will be the transfer matrix. So this will be our transfer matrix. Now let's see now we have solved the first question. Let's move toward the question number 2. Okay, here question number 2. Here is a simple question. Eigenvalues of this transfer matrix, right? Eigenvalues of this transfer matrix. So T is equal to 1 e to the power beta j, and assume that beta j equal to x, that means 1 x. So its eigenvalue will be, if there is a eigenvector v, if I multiplied by that eigenvector, it will give me lambda v. So now if you calculate this, t minus lambda into v is equal to 0, that means if v not equal to 0, then t minus lambda, its determinant should become 0. Now here there is a lambda I should be there. I is the identity matrix. So t minus lambda this will become 1 minus lambda 1 0, x minus lambda is equal to 0. So this will become 1 minus lambda into x minus lambda. So this should be 1, not 0, this should be 1. Minus 1 is equal to 0. So lambda square minus x plus 1 lambda and plus x minus 1 is equal to 0. Now by applying Sidor-Acharya rules, we will get the value, the two roots of the lambda, which will be plus x plus 1 plus minus root over of p square x plus 1 its square minus 4x minus 1 by 2, which is x plus 1 plus minus x square plus 2x plus 1 plus 4 minus 4x by 2 by 2. So this will become x plus 1 plus minus root over of x square minus 2x plus 5 by 2. These will be the two eigenvalues of this matrix. Okay, now let me, so I have solved this question. Now let me bring the third question. So question number 3, the canonical partition function for the above model for z for n much greater than 1. As we have as I have write it already, the partition function will be nothing but the trace of t to the transfer matrix to the power n, and we know that the trace of t to the power n will be the eigenvalue of, if there are two since this is a 2 cross 2 matrix, then for t to the power n there will be two eigenvalues. Suppose they are lambda 1 and lambda 2. Trace will be the eigenvalue sum, and we also know that if the trace of t is lambda 1, then the trace of t to the power n will be lambda 1 to the power n and lambda 2 to the power n. Now if we used these two here, we will get the trace, since the partition function is nothing but the z equal to trace of t to the power n, which is mean lambda 1 to the power n plus lambda 2 to the power n. And suppose that my lambda 1 is greater than lambda 2, that means lambda 1 is x plus 1 plus root over of x square minus 2x, x square minus 2x plus 5 by 2, and lambda 2 will be x minus 1 and x plus 1 minus x square minus 2x plus 5 by 2. So that means if I take common lambda 1 plus lambda 2 by lambda 1 to the power n. Now if I, since lambda 2 by lambda 1 should be less than 1 because lambda 1 is greater than lambda 2, that means limit n tends to infinity, lambda 2 by lambda 1 to the power n should goes to 0. That means for n much greater than 1, we can safely say that partition function is nothing but lambda 1 to the power n, which is x plus 1 plus root over of x square minus 2x plus 5 by 2 to the power n. So that is the answer of the question number 2. Now let's bring that the question number 3, which is related to the previous question. Question number 3, question number 4, the average energy. Now there is a formula, or let me write it. Since z equal to partition function is nothing but summation of e to the power minus beta h for all possible combination of the particles sitting at the I state, the average, and we also know that the probability of remaining in the state I is nothing but e to the power minus beta epsilon I. If the energy in the ith state is epsilon I, then the probability that a particle will be there in the ith state is e to the power minus beta h by summing over I e to the power minus beta h. That means the average energy of the particle will be, if there are ni number of particles sitting there at epsilon energy, the total number of energy at the state I is ni epsilon I, and probability of the particle is there is pi. So this will be the average energy, all the possible combinations of ni, and it will become summation of ni epsilon I e to the power minus beta epsilon I ni by summation of beta h. Now from here you can tell that what this quantity is. Actually this quantity is nothing but the minus del beta of ln z, where z is e to the power minus beta h. So del beta of ln z will give this quantity. So if you know the partition function and you take a derivative with respect to beta, you will get the average energy. Now since we know the from the previous question we know that the partition function z, then we can tell what is the average energy. So let me do the ln z will become here n x plus 1 plus root over of x square minus 2x plus 5 by 2 ln should be there by 2. Now let me minus del beta of ln z will be minus n x plus 1 plus root over of x square minus 2x plus 5 and derivative with respect to beta, del beta of x plus 1 by 2 and by root over of x square minus 2x plus 5 2x del beta minus 2 del x del beta, and we know that x equal to the power beta j, that means del x del beta will be j e to the power beta j, so that means minus n j e to the power beta j plus 2 cancelled, it will be the e to the j e to the power 2 beta j minus e to the power j e to the power beta j e to the power beta j by root over of these terms. So okay, so let it be right in terms of, so it will be e to the power beta j, that means e to the power beta j means x, so e to the power j x. So let me write it in terms of x. It is actually minus n jx plus is x jx square minus jx root over of x square minus 2x plus 5 by x plus 1 plus root over of x square minus 2x plus 5 minus n, if I take common jx, by root over of x square minus 2x plus 5, it will give that x minus 1 plus root over of x square minus 2x plus 5 by x plus 1 plus root over of x square minus 2x plus 5. So that is that. So this will be the average energy of the system. Now we have solved this question also. Now let's go towards the next question. Insert question 5. Now let's 5. This is an interesting question. Let's solve the question number 5. Okay. Now for the above model, add a magnetic field. In the above system, we have added another magnetic field. Then it is asked that what is the effective mean field Hamiltonian, right? So first write these terms. H equal to minus J summation of I equal to 1 to n si plus 1 plus h into summation of I equal to 1 to n. right? Since we can, in the mean field level, we can take these as SI, a mean field, and the and the fluctuation about the mean field is very small. Then we can write SI minus mean of SI plus SI. Let me write it for the moment. SI, average of SI is M, so SI minus M plus M. Now if you write SI plus also like that, so SI plus 1 will be SI plus 1 minus average of SI plus 1 plus SI plus 1. Since the mean field of the mean of this I and I plus 1, the field that is there for ith side and I plus 1 side will be same. That means the mean of SI and I plus 1 will be same. That means these also be the same as summation of average over SI, which is M. That means it can also be written as SI plus 1 minus M plus M. Now we multiply these two terms, SI plus 1, which is there in the above, so it will SI minus M plus M into SI plus 1 minus M plus M, which is SI minus M into SI plus 1 minus M. This multiplied with this M SI minus M, this M SI plus 1 minus M plus M square. Now since this is the fluctuation SI minus M, the fluctuation in SI and the fluctuation in SI plus one side, that means this is in the order of the fluctuation square. That's why we can safely neglect, if we are working in a mean field level, we can safely say that these fluctuations second order will not matter because SI minus M is itself very small, so we will keep up to only first order. Then we can write it M square plus M, neglect this term, M SI minus M plus M SI plus M minus M plus M square. So this is M square I have kept in the first term. So now if I open these things, so it will be M SI plus SI plus 1 minus M square plus M square, so it will be cancelled. That means M SI plus 1. So if we write it here, then H will become equal to minus J summation of M SI plus 1 minus M square summation of I and plus H summation of I SI. Since this is I n is huge, we can write SI plus 1 as SI. That means this will become SI nearly equal to SI plus 1. That means we can write it as minus 2J summation of I equal to 1 to N M SI minus there is a J is there also, so J N M square plus H summation of I SI, so J N M square plus H minus 2 MJ sum over I SI. So now you can see that we can write H a constant term plus adding some term which is called H effective magnetic field into the SI. So we have write the effective mean field Hamiltonian. So this will be the effective mean field Hamiltonian. So the effective mean field Hamiltonian will look like this, where we have take two assumptions. First assumption is that the fluctuation, that means the variation of SI about its mean is very small, so that we can neglect the second order term with respect only keeping first order term. And secondly, since there is a large number of particles, that's why the fluctuation is very small, we can replace SI by SI and SI plus 1 by SI plus 1. It is not approximation also, it's not an approximation also. So these both summation of I SI should be same as SI plus 1. So whatever you write, either SI or SI plus 1, the both summation will give you the same result, because the total number of particles are very huge, n is very large. That's why you can replace SI plus 1 by SI and you can write this. So this is the mean field Hamiltonian. Now let's move toward the insert the last question of this assignment. So okay, question number 6. What is the transcendental equation for the mean field solution? We know that the average magnetic field SI, average momentum will be minus del beta H effective of ln z. So if we know that what is the H effective and what is the total Hamiltonian, we can say that what is the mean field, what is the what is the mean momentum, mean magnetic momentum. So let me check it once. Okay, is that. So now we have to calculate the partition function. So let me calculate the partition function. Partition function is all the possible combinations of SI's e to the power minus beta h, which is to the power SI e to the power minus, so this first term will be plus j n square m, second term will be e to the power minus beta h effective. So this is, there is a negative sign should be there, h effective summation of I SI. Now we can take this multiplication first, I equal to 1 to n, and we'll do the first summation, then we'll do the multiplication j n square m and all possible combination of SI's e to the power minus beta h effective SI. And we know for the above particle, for this particle the SI can only take 0 or 1, the value between 0 or 1. Okay, in the first question, the 0 and 1, SI can take value 0 and 1. That's why it will become jn square m 1 to n. This will become, first if we put 0, that means 1, and if we put 1, it will become plus e to the power minus beta h effective. And since this term is no longer depend on the particles, which particle is on which side, that means it will become 1 plus e to the power minus beta h effective to the power n. Now the total average SI will be, so there is 1 by n minus 1 by n minus 1 by n del beta h effective of ln z. So this will nn, so the first term not contains any beta h effective, so it will not contribute, the only second term will contribute. So minus n by n del beta h effective ln 1 plus the power minus beta h effective. So minus 1 into 1 by e to the power minus beta h effective into minus 1 into to the power minus beta h effective. So it is 1 by, if I take if I multiply upside and downside by e to the power beta hf, it will 1 plus e to the power plus beta h f. So this is the m, or the total magnetization, the magnetization or the average of spin is equal to 1 by 1 plus e to the power beta, and h effective means h effective is h minus 2 mj, h minus 2 mj. So this is the applied magnetic field, and this is for the interaction between the particles. So this is the answer. This is called the transcendental equation, which will give you the value of the magnetization. So that's it. Now we have solved these things, and that is that. Now let's do another thing in today's class. So we have we did only the Ising model. We did only the Ising model for periodic boundary condition, periodic boundary condition. But let's do, if instead of periodic boundary condition we have a Ising model of infinitely long chain of spins, that means the total number of particles, instead of using this boundary condition that we have used explicitly, the boundary condition is n plus 1 equal to s1, instead of that, if you say there is a long chain of Ising spins, that means if we take a large number of sides, that means n equal to infinity, what will be the, can you solve the Ising model and what will be the answers? So let's try that. So we know that the Ising model, Ising model what is the value for Hamiltonian? It is minus j summation of si plus 1 I equal to 1 to n, but since n is very huge, very large, so that's that. Now what is the Ising, what is the canonical partition function? Canonical partition function will be all possible combinations of the spins let me check it once, there is any question or okay, si. So this is e to the power plus beta minus beta h minus beta h, so this is summation of si e to the power plus beta j summation of I equal to 1 to n si plus 1, right? This is that. Now the total number of particles, or you can say that the summation at the end point, what why we have taken this boundary condition, because at the end point we don't know what happens, but in place of for infinitely long chain of Ising spins, the boundary condition is taken care, because n, if n tends to infinity, then means n plus 1 also tends to infinity. That's why for infinite long chain the boundary condition is automatically taken care, that there is no edge, actually edge is at infinity. Now we can do one thing, the multiplication first, then summation, first summation then multiplication, we'll get e to the power beta j si plus 1. Now if since si can take values only, si can take value plus or minus 1, that means it will become I equal to 1 to n. If let's put the value of si plus 1 and minus 1, the first term will give beta j plus 1 plus 1, second term plus 1 minus 1 minus beta j, third term minus 1 plus 1 minus beta j, and fourth term minus 1 minus 1, which will give beta j, which is does not depend on the site or the position, the site of the spin. That means it does not depend on I. That means this multiplication will become e to the power, it is 2 e to the power beta j plus e to the power minus beta j to the power n. Now this means 4 cos hyperbolic beta j to the power n. Now if you see that these and the partition function, this and the partition function we get from the periodic boundary condition, periodic boundary conditions are different from each other. For the periodic boundary condition, what we get, the periodic boundary condition we got, let me check it. For periodic boundary condition, okay, what is the value of z? Yeah, so we got this thing. For periodic boundary condition, we get the z is actually for h equal to 0, we for h not equal to 0, we don't know. For the periodic boundary condition, Si Sn plus 1 equal to S1, the Z is for non-zero magnetic field e to the power beta j cos hyperbolic beta h plus root over of e to the power 4 beta j sin hyperbolic sin beta h its square plus e to the power minus 4 beta j. Now for h equal to 0, by 2, okay, there is a by 2 and to the power n also there. This is the z, and second is e to the power 2 beta j minus root over of e to the power 4 beta j plus sine square beta h plus e to the power minus 4 beta j by 2 to the power n. Now for h tends to 0, sine square beta is 0 and cos beta is equal to 1. It will give e to the power 2 beta j plus e to the power minus 2 beta j so where I okay, these two factor is because of these two factors should not be there, so this is basically 2 beta j, this will be 2 beta j, this is beta j, this is 2 beta j, this will be 2 beta j. That means e to the power beta j e to the power beta j plus e to the power minus beta j by 2 to the power n plus e to the power beta j minus e to the power minus beta j by 2 to the power n, that is cos hyperbolic beta j plus sin hyperbolic beta j to the power n to the power n. Now you can see from here that these two results are not matching, because if I consider, instead of periodic boundary condition, if I consider the infinite chain, these two, one is z equal to 4 cos hyperbolic beta j to the power n, and another from the periodic boundary condition cos hyperbolic beta j to the power n plus sin hyperbolic beta j to the power n. But the beauty is, if you take the limit n tends to infinity, that means thermodynamic limit, these two matches exactly. In the thermodynamic limit, you can take common of cos hyperbolic beta j to the power n 1 plus this will be tan hyperbolic beta j to the power n, and since we know that the tan hyperbolic beta j is always less than equal to less than 1, that means this term will go to 0 at n tends to infinity, and the partition function will become cos hyperbolic beta j to the power n. So then only in the thermodynamic limit, when the n is large enough, it is whatever you choose, whatever periodic boundary condition you choose, these two will give you the same result. That's that. This is for the Ising model for periodic, not for periodic boundary condition. It's for it's for a infinite long chain. So this will look like that. Now let's move towards the another questions. Let me bring the other questions. First solve this question. Okay, let me bring it there. So let's solve this question. Question 1. Imagine 2n labeled sides on a line. At each side there is a spin that can point up or down. If it points up, its energy is +1, and if it is down, its energy is -1. Find the entropy of the system if the total energy is 0. Right? That means there are a side. There are 2n number of sides are there. This is 1 2 3 ... 2n number of sides, and the spin can take up value or down value, any of one. So any configuration it takes, up, down, up, down. Now here it is asked, find the entropy of the system if the total energy is 0. Now from the question we know that if a spin is in up direction possess energy +1 and down direction is possess energy -1. That means for total energy to be 0, we need exactly equal amount of upward spin and downward spin. That means if there are total number of particles in n, then out of n1 number of particles upward direction and n2 number of particles downward direction, then for total energy will become 0 when n1 is become equal to n2. That means n1 plus n2 become 2n. Since n1 equal to n2, that means 2n1 is equal to 2n. That means n1 equal to n2 equal to n. That means total half of the particles spin should be in upwards and half of the particles spin should be downwards. Now how many ways these can be achievable? So we know that the ways, that means the total number of microstate, which is 2n factorial by n factorial into n factorial. Then what will be the entropy? It is asked entropy. Entropy will be S equal to k beta ln omega. Here we always assume that kb equal to 1. That means ln omega, which will be ln 2n factorial minus ln n factorial minus ln 2n factorial. Let's use the Stirling approximation. What is the Stirling approximation? For large n, ln n factorial will be n ln n minus n. So if we use that here, it will 2n ln 2n minus 2n minus 2n ln plus 2n cancelled, so equal to 2n ln 2n minus ln n, which will be 2n ln 2n by n, which is 2n ln 2. So these will be entropy. So one interesting property you should notice that the entropy, as we know, the entropy is an extensive function. That means the entropy should depend on the total number of particle is there in the system. That means it should proportional to the total number of particles. That means n. Here you can see that the entropy is actually proportional to the directly proportional to the total number of particles. So this is that the entropy we have calculated. Find the canonical partition function at temperature T. Right, let's find that. What is the canonical partition function? Canonical partition function, we know that canonical, what is the canonical partition function? Z equal to possible combinations of the particles minus total e to the power minus beta is total number of energy. Here the combination of the spins is there. That means summation of all the spins. And what is the energy? E to the power minus energy. Energy is same. If it is up, then plus, down is the negative. That means if there are n one number of particles, and okay, so that means if n number of particles are there, ni number of particles are there, its energy is Fi. So okay, so if let me write it a proper way. So ni sigma I. Suppose that ni particles are there with spin sigma I in value, sigma can take value plus 1 or minus 1. So ni number of particles are sigma I, then we can write it like that, and summation of all i's, only two states there, but summation of all I. So all ni sigma I. Okay, so here it should be ni, so let me check it. Let me check it whether I'm correct, wrong or right. So let me write it in a proper way. Okay. Proper way. So Hamiltonian, you can write it as summation of I equal to 1 to 2n sigma I, where sigma I can take value between plus 1 and minus 1. That means if sigma is upward, then the energy will be plus 1, and if it is downward, its energy will be minus 1. Then Z will be the all possible combination. So the Z will actually, Z is the trace of that. That means this. So this is possible combinations of sigma i's, here Z e to the power minus beta summation of I equal to 1 to 2n sigma I. Now we first sum over the possible combinations of sigma i's, then we'll multiply the total number of particles. So e to the power minus beta sigma I sum over all possible combination of sigma i's. So we know that what sigma I can take value plus 1 or minus 1. That means it will give you I equal to 1 to 2n. So if sigma I take plus 1, it will become minus beta, and if we take plus 1, it will minus beta, minus 1 plus beta, so it will be plus beta. So that's that, and it means, and it does not depend on I, so we can write it simply e to the power minus beta plus e to the power plus beta to the power 2n. We know that e to the power beta plus e to the power minus beta by 2 is equal to cos hyperbolic beta. So you can write it 2 cos hyperbolic beta to the power 2n. So it will be its the canonical partition function at temperature T. Find the average energy. So we know that the average energy is nothing but minus del beta of ln z, right? So del beta of ln z, that means first ln z will minus 2n del beta of ln cos hyperbolic beta plus ln 2. I just did that. I take ln. If I take ln here, so the 2n will this like that, and first term will be ln 2 and the second term will be ln cos hyperbolic 2. So I write that way. So this term will cancel because it is a constant. So it is minus 2n cos hyperbolic beta sin hyperbolic beta, so minus 2n tan hyperbolic beta. So this is the average energy of these 2n particles. And another interesting thing, so let me go and in the previous in the beginning of this tutorial, where I have told you that the canonical ensemble system can be represent in canonical ensemble when the partition function is needed for describe the system. Since we and for the microcanonical system, the entropy is needed for describe the system, then there should be such a thermodynamical thing which will be replaced for describe the system in canonical partition function. And we know that since this is nothing but the Legendre transform of the microcanonical system, that means the Legendre transform of entropy should be the describing potential or describing things for the canonical ensemble, and it is happens to be that the Legendre transform form of the entropy is the free energy. Entropy is the free energy. So that since the partition function Z is the canonical is the Legendre transform form of the total number of microstate, then the and free energy, and we know also the free energy is the Legendre transform form of entropy. So F should be the free energy should be the k beta T of ln Z, and if you calculate the entropy and average energy separately, you will get that the free energy takes the form F equal to k beta T. So the ln Z is important because from ln Z you can calculate the free energy, and from free energy you will get the all thermodynamic quantity. So that's that. Now let me bring another question. Okay, so let me solve this question. So a system consists of n weakly interacting particles at temperature T sufficiently high so that the classical statistical mechanics is applicable Each particle has mass m and its free energy to perform one-dimensional oscillation and about its equilibrium position. Calculate the heat capacity of the system if the restoring force is proportional to x cube. If the restoring force F proportional to x cube minus x cube, since it is restoring, it should be minus x cube. So F equal to, suppose that k is the constant and x cube, then the potential energy will become integration of minus f dx, which will become 1/4 kx to the power 4. So potential energy we know, the kinetic energy will be, kinetic energy we know as usual, p square by 2m. Since we know the kinetic energy and potential energy, that means we know the total energy of the particle which is at the position xi and pi. Then we can write the partition function. Since pi and xi is a continuous in classical mechanics, we can write an one dimension dx dp by the h, the smallest area in the phase space. Since we want to count the total number of microstate is there in this volume dx into dp, we need a count, we need a smallest area. By using that smallest area we can count the total number of microstate. That's why we divided by the h. So dx dp into e to the power minus beta h. H is the Hamiltonian, and we know what is the value of this Hamiltonian. It is nothing but only I'll calculate only for one particle, and the n particle will be z to the power n. The summation of for one particle 1 by h dx dp, both will x and p both will go from minus infinity to plus infinity. E to the power minus h is p square by 2m plus 1/4 kx to the power 4. So e to the power minus beta h means beta by 2m p square minus beta half kx to the power 4. That's that. So there will be two integration 1 by h, x equal to minus infinity to plus infinity dx e to the power minus half beta k x to the power 4. This is the one integration. There is another integration which will be plus infinity dp e to the power minus p square by 2m. 1 beta is sitting there. Okay. So let me separately do this integration. First let me do this integration. So this integration is minus infinity to plus infinity dx e to the power minus half beta k x to the power 4. Let's assume that beta k by 2 beta k 2x to the power 4 equal to z square. That means x to the power 4 equal to 2z square by beta k, which means x equal to 2 by beta k to the power 1/4 z to the power half, right? And x equal to that, and z equal to beta k okay. So what will be the dx? Value of dx will be 2 by beta k to the power 1/4 half into 1 by z to the power half into 2z. So in place of x we will replace the z, we will get minus infinity to plus infinity dx half 2 by beta k to the power 1/4 into dz by z to the power minus half e to the power minus z square. So half into 2 by beta k to the power 1/4 into minus infinity to plus infinity dz z to the power minus half e to the power minus z square. This integration you can write it as in terms of gamma function. We know that integration minus into plus infinity dz e to the power minus z square z to the power 2n minus 1 is equal to gamma n. So here z 2 to the power n minus 1 equal to minus half, that means 2n equal to plus half, and n equal to 1/4. So that means this integration equal to gamma 1/4, which is a basically constant. So that is gamma 1/4 by 2 into 2 by beta k to the power 1/4. So this will give that, and let me do this integration. So minus infinity to plus infinity gp e to the power minus beta p square by 2m. So in the similar manner we took beta p square by 2m equal to some y square, which keep p equal to root over 2m by beta into y. So that means dp equal to root over 2m by beta into dy. So put it here. So minus infinity to plus infinity root over of 2m by beta e to the power minus y square dy, which will give root over 2m by beta minus infinity to plus infinity dy e to the power minus y square. So from the definition for the gamma function, which is this definition of gamma function, which is this, we know that 2n minus 1 equal to 2n minus 1 equal to here 0, that means n equal to half. So that means this value is gamma half, which is nothing but root pi, or you can write it as gamma half also. So we kept it gamma half. So this is gamma half into root over 2m by beta. That means our z for a single particle, z will be 1 by h into this. So 1 by h into the value of first integral. The value of first integral is gamma 1 by 4, gamma 1 by 4 by 2 into 2 by beta k, 2 by beta k to the power 1/4, and the second integration value is gamma half into root over of 2m by beta. Now, so what we have to calculate? So that's that. So now calculate the heat capacity of the system. So to calculate the heat capacity, we need the average energy. So for average energy, we have to do that minus del beta of ln z. So we have to calculate the ln z. Ln z will be ln this all constant together. Let all constant together 1 by h gamma 1/4 by 2 and 2 to the power 1/4 into 2 to the power half into m to the power half k to the power 1/4 is there anything 1 by h gamma 1/4 by 2 to the power 1/4 into 2 to the power half into n to the power half this is the all the constant that does not depend on beta, because I want to derivative with respect to beta. So the second term will be plus, or this is actually minus minus ln half. Okay, right, let me write it here so it will be clear. So plus ln 1 by root beta into 1 by beta to the power 1/4. 1/4 plus half equal to 4. 1 plus 2, so that means 3/4. There is some constant which does not depend on beta, does not depend on beta, plus ln 1 by beta to the power 3/4. So that means a minus 3/4 ln beta. So if I integrate it out, so ln z by del z, what I will get equal to, oh sorry, not del z, del beta, I will get minus 3/4 del beta of ln beta, which will give me minus 3/4 beta. That means the total energy, average energy, will be minus del ln z del beta will be plus 3/4. We know that 1 by beta is, that means k beta t, so 3/4 k beta t. And since it is a energy for a one particle, for one particle, so what will be the energy for the n particle? N particle energy will be En, which will be plus 3/4 n k beta t. What will be the specific heat in constant volume, which will be del t of n e, which is nothing but 3/4 n k beta. So this will be the specific heat for the, this will be the specific heat for the particle in the classical limit, when the temperature is classical and when the restoring force is x cube. So that's it. That's the thing. Okay. This another thing I want to do is I want to do another calculation, simple calculation. Insert another question. Let insert another question. So insert image. Okay, not image, it is there in okay, it is there in this questions. Another question I want to solve. So I want to solve this question. So let me take this question. Okay, I'll solve this question here. Okay. Let me solve this question. Consider a system. Here it is asked that consider a system of two non-interacting classical particles which can occupy any of the three energy level with energy value E equal to 0, E and 2E having degeneracy. Calculate the mean energy of them. So we know that the rule that we have to calculate first the partition function. So let me write it, the rules of calculate the average energy. So first rule, calculate the Hamiltonian of the system, and if you get that, you calculate partition function at temperature, suppose T and 3, then you take a derivative with respect to beta, which is beta is nothing but 1 by k beta T of ln z, which is equal to average energy. So this is the machinery to calculate average energy. So let me calculate the average energy. So first Hamiltonian, that means energy, we already get that energy. Then the partition function z will be, so for with energy 0, so that 1 is there, so 1 into e to the power energy minus beta into 0 plus 2 degeneracy is there, 2 into e to the power minus beta to what is the energy, this E, and what is the energy E, and what is the only one particle is there. So there are two system of non-interacting classical particles. So I assume that only one particles are there. So one particles either can sit there or sit here, the minus beta energy V, so beta into 2E. So that means z equal to, it is 0, so it is 1 plus 2 e to the power minus beta E plus 4 e to the power minus 2 beta E. Now what will be the average energy? Average energy minus del beta of ln z, so minus del beta of ln 1 plus 2 e to the power minus beta E plus 4 e to the power minus 2 beta E is 1 plus e to the power 2 e to the power minus beta E plus 4 e to the power minus 2 beta E. So first derivative with respect to this minus beta, so it will give minus 2e to the power minus beta E minus 8 e to the power minus 2 beta E. So you take common of 2e into another thing I want to say here, so plus 2 e to the power minus beta E minus E plus 2e into 4 e to the power minus 2 beta E by 1 plus 2 e to the power minus beta E plus 4 e to the power minus 2 beta E, 1 plus 2 e to the power minus beta E plus 4 e to the power minus 2 beta E. Here I want to say that from here you can see that the probability of a particle staying at energy E will be nothing but the 2 e to the power minus beta E by 1 plus 2 e to the power minus beta, and here also, so that means the probability of a particle remaining at energy EI will be nothing but the degeneracy of that energy e to the power minus beta of that energy by summing over this GI EI e to the power minus beta EI. So this is the probability that a particle has energy EI. So that's that. So then now we have calculated the mean energy. Mean energy is nothing but this plus E 2 e to the minus beta e plus 2e for this. So that's that. Now this we have solved the question 4. Now let's okay, so let's solve another question, then insert another question. Okay, it is not there here, so so let me have another simple question. This question I will solve. The entropy of a simple and interesting question. Let me solve this question. Here it is asked that entropy of a classical harmonic oscillator that has an energy between 0 to E. So what will be the entropy of the classical harmonic oscillator? So we know that to calculate the entropy we have to know what? We have to know one, the total number of microstate. Total number of microstates. And if we know the total number of microstate, we apply the Boltzmann law, which we know that A is equal to k beta into ln of omega, which is the total number of microstates. So if we know the total number of microstate, we actually know the entropy. So that means we have to here somehow calculate the total number of microstate. Total number of microstate, if there is a classical harmonic oscillator, it moves in the phase space, and we have to calculate the total number of microstate between 0 to E. And we know that for the counting, the smallest in the 1D is in one dimension. So the smallest area or volume of one microstate is H. So 1 by H equal to 1 by H, the total number of microstate, is the total area. Or let me write it. The total number of microstate will be the smallest area per one for one microstate. The total area covered by this dx dp x equal to something where this total energy that means x square half m omega square x square plus p square by 2m, it is the energy of that harmonic oscillator, should less than it remain between 0 to E. So this is the total phase volume that it will cover, and for a single microstate, a single microstate covered the phase space is H. So total area by the area which is the minimal for a microstate, if you divide by that H, you will get the total number of microstate. Now this integration is the area of this curve. So if you write it in this way, half m omega square x square plus p square by 2m equal to E, you can draw a ellipse. So if you can do it, x square by 2e by m omega square plus p square by 2me equal to 1. That means this is a ellipse. So and the particle which has the energy E will remain on the boundaries of this ellipse, but the particle which has energy between 0 to E, they will remain inside this ellipse, right? So remain inside remain inside this ellipse. So if that particle will remain inside the ellipse, so what is the total area that ellipse will that the particle will cover, that the area under this ellipse? So we know that the area under the ellipse is pi a into b. A is this and b is this. A is this and b is this. So here what is the value of a? We know that equation of the ellipse, x square by a square plus p square by b square equal to 1. So a equal to root over of 2e by m omega square, and what is the value of b? B is root over of 2me. So the total area covered equal to pi a into b. A is 2e by m omega square, b will be root over 2me, and this is pi into 2e pi omega. Okay, so my total number of microstate will be 2 pi into e by omega by h. We know that h by 2 pi equal to h cut, so that means e by h cut omega. So this will be the total number of microstate which will be there if the particle possesses the energy between 0 to e. So what will be the entropy? Entropy will be kb ln e by h cut omega. Now one thing you should notice that, so here we use the h cut and h. You can think that this is a quantum mechanical thing, but I want to emphasize that, so this age is nothing, this age happened to be the Planck constant, but here we don't need any quantum mechanical assumption. Here we need only for the counting purpose, since we want to count the smallest grid, the total number of means we want to count the total number of microstate. That's why we need a constant which is the smallest area needed for a microstate. So that means you will say that if the particle is roaming around inside the area h, you will call the total state as a microstate. So one can say that you can further fine grid the h, further zooming out into the h, and you can say that this will be the smallest area that will be that I will define as a single microstate. You can do so, but if so that's why this h for classical statistical mechanics, this h is a constant, but in quantum mechanics it automatically coming that the area, minimum area that is there is h, because of the uncertainty principle. So this is that, and this came from classical stat mech, nothing to do with quantum mechanics, because here h is an arbitrary constant, arbitrary small value which is a constant for the statistical mechanics. So that's that. This is a very beautiful result, because you know that this e by h cut is telling you that the total number of total means if the h cut omega, so total number of microstate is nothing but the energy by the smallest energy, which is h cut omega. So that's that is there. So since time, so this today I have planned to do up to this. So I have did all the things that I want to do in this tutorial. So if you have any questions, so you can ask me or you can leave. Okay, so that's it. So thank you for coming. I am ending this tutorial here.